Today we'll be running a nonlinear dynamic solution 402 of a one-cylinder engine. We'll begin by creating our solution files in the Nastrian solver environment, and we'll set up our solution 402 multi-step nonlinear kinematics with large displacements on. Next we'll create a nonlinear dynamic subcase with 50 increments and an end time of 1 second. Now we'll begin in our idealized part, where we'll get an associative copy of our geometry. Now I don't need these piston rings for my simulation, so I'm going to remove them with the replace face command. Now also we're going to use symmetry, so I'll split my connecting rod and piston by a midplane. Then we'll bring half of those bodies into our FEM. Now we're ready to mesh. We'll create a TET 10 mesh on our components. Here you can see the mesh recipe. Next I'll assign a material. And now we'll create our bearing at the end of our crank here. I'm going to simulate that with a point-to-face connection with an RBE2. And later I'll assign a constraint that will allow that to rotate. Now we'll create our kinematic universal connections. We have a number of different types of kinematic connections. I'm going to create it with the targets being spider, spider for target 1, target 2, and legs of COG for my method of creation of that spider. So the center point will be at the center of gravity of my leg nodes. Next we're going to specify an axis, and before we do that, let's take a look at the types of connections that we have. We have a user-defined one, which is general. I really want a revolute, and you can see here that the revolute is going to leave DOF4 free. So that means rotation's about X, so we want X to be the axis of revolution of our joint. So keeping that in mind, I'm going to create a CSys using the X-axis, Y-axis origin method. I'll select my origin at the center of the arc. Then I'll select my X-axis to be the CSys of that edge. So that goes along the axis. Next I'll use 2 points to define my Y-axis, where I'll go from the center of my connecting rod down to the center of my crank. And that fully defines the coordinate system. Alright, so we won't put in any physicals or any friction for that connection, and we'll move on to our next one. So in the same fashion, we'll create a kinematic connection. Similar targets, spider legs of COG and spider legs of COG. Create another Cartesian coordinate system for our degrees of freedom for our connection, using the same method, X-axis, Y-axis origin. And 2 points for our Y-axis. And here, to make it easier to pick that arc center, we'll go ahead and specify that we're looking for an arc center. Same thing for the specify to point. Alright, we'll create another revolute that has DOF4 free. And now you'll notice that our universal connections are not yet realized. That's because we need to specify what types of elements we want to use. So we're going to use a CJOINT plus RBE2. CJOINT is a special element that's only available in solution 402. That will allow us to simulate a mechanism. Next we'll go to the sim where we'll assign some constraints. Our first constraint is we're going to leave rotations free about the z-axis in the global reference frame, which is existing. I could specify a local one if I wanted to, right in this dialog, but we'll use the global since it lines up. Next we'll create a constraint on our piston cylindrical wall where it is in contact with the bore, and we'll go ahead and fix degrees of freedom 1 and 3, which is X and Z, and we'll also exclude the edges. And the reason why is because we're going to create a symmetric constraint on those faces, and we don't want to have any overlapping constraints. So here for some reason I'm not getting a pre-selection highlighting on that face, but I'll go ahead and pick it anyway, and you can see we've got two objects and the constraint goes on correctly. Alright, so next we'll assign a load. We'll put gravity in the minus YC direction, so that will pull the piston down, and we'll go ahead and save and solve. So now we have a nice solution monitor which gives us the progress of our solution. You can see we're heading towards a 1 second solve time, and then we have a nice solution control monitor which shows us graphically the results at each time step. So we can see that our model is behaving as we expect. I'll go ahead and pause the video for the rest of it. You can see it takes a little under 3 minutes to solve to completion, and then we can post-process our results. We'll go ahead and take a look at our displacement results and animate those across our time steps. Kinematic universal connections make it easy to simulate a mechanism with Simcenter 3D and our nonlinear kinematic solution 402.